So I'm going to be talking about iteration in Python. And I'm a professor of computing science at the University of Alberta, teach Intro to Software Engineering. One of the warnings is this talk is not completely Pythonic, and it's not completely idiomatic. If you want to do it right, well, there's other ways to do it. Okay, iteration. So programming is generally useful because we can repeat tasks. Iteration tends to be one of the fundamental building blocks of why we actually build software and why most programming languages exist. Usually we want to repeat something. Iteration usually refers to repetition in general. So we want to repeat something, we want to do it more than once. In mathematics, iterating a function means to apply it repeatedly. In programming, it means any method of repetition. Throughout this talk, I'll be using the concept of a block. A block is a chunk of code. It's usually the part that you repeat, and it usually follows scoping rules. So usually it has access to anything within its scope and maybe some things in the upper scope that it was invoked in. A condition is an expression that evaluates a true and false. Usually these conditions are used to determine whether or not we should carry on looping, whether or not we should stop looping or even loop any at all. Other concepts that are important are strictness. Python is a strict language. It does everything you tell it to do, and it will do it in that order. A lazy language will usually do something when it gets done. Some features of Python are lazy, some are not. In order tends to mean we execute things in a specific order. Out of order means we can execute things in whatever order we want. Dependency means that one value depends on another. Now this is important for looping. So the first loop we deal with in Python is the while loop. So the while loop allows us to repeat a block until a condition is met. Generally, you choose to use a while loop because you don't know how many elements you have, or you don't, for instance, when you're reading lines from a file here, so I've got count equals 0, while system standard in read line is not equal to the empty string, count plus 1. While we do that, we're basically counting the number of lines we read. When I execute that code, I could enter in 0 lines, I could enter in 100 lines. You don't know. So a while loop is good when you don't know how many times you do something. The structure of a while loop is you have a condition, and then while that condition is true, you have a block. That block is run while that condition is true, and when that condition evaluates the false, in this case, it will be the first one after it runs one time. Then it won't run this block again, and you'll be here. At this point, condition in this case will be false. Sometimes you might do some mathematics and you're not sure when to quit, or you're not good at counting or something like that, so you're not sure how many times you're going to iterate. So in this example, we have x equals 100, and while x is greater than 1, we divide it by 3. So this means after a while, it'll eventually stop, because eventually we'll divide a value and we'll get a value less than 3. Like the last value should be about 0.4. So while loops are good when you don't know how many times you want to loop, or when there's a definite condition that you know when you want to end. The other iteration construct you're going to use a lot in Python is the for loop. It allows you to iterate basically over any iterable collection, like a collection or a range, and you iterate in order, one after the other. In this case, we've got a sum equals 0, and then we're re-implementing the sum function using this for loop. And for I equals range 1 to 10, we add that to sum. Now if you look here, we've got sum here and sum here. So sum here is a dependency, right? The condition of this for loop is really that there's elements to iterate over. So we've got a for loop body right here, and it's got a dependency there. And we got the same dependency here, and the same kind of dependency here. So we can have a full range if we just want to iterate over 1 to 10. We can have a X range, which in Python 2.7 is a lazy range, where it doesn't make a full array, it just makes something that's iterable. And then we add them. If we get the sum of that, we get a very large number. In this case, we're concatenating using a for loop. We're iterating over a list here, ABC, and we'll eventually get a string that says ABC. So the for loop lets us iterate over known values and known ranges. It's good when you know exactly how many elements you have, or when a collection will dictate how many elements to iterate over. How do we iterate over things? Well, we use an iterable. The most important method in the iterable is the next method, and the next method produces the next value, or it raises an exception at stop iteration. This iterable that I show here will only return the even indexed elements of a list. So here I provide only evens with values from 1 to 9, and it will print 1, 3, 5, 7, 9. So those were only the even indices, okay? And you also want to implement this one. And the way you stop the iteration is to raise stop iteration. That means that you can write anything that fits into a for loop. So this part of the for loop, anything that is an iterable can be iterated over using a for loop. So it's a nice little interface. Another method that is common to most programming languages that allows you to iterate is recursion. Recursion, it allows for arbitrary flow control by calling yourself. So in this case, I've defined rec sum, a recursive sum, and I iterate through all elements of the list, adding it together, and it recursively evaluates. So it'll first get L is 0 plus the recursive sum of the rest of the list. So L is 0 plus L of 1 plus L of 2, all the way through to the last one where it'll add 0 to the end. So recursion allows you to iterate in pretty well any kind of manner you want, and it's good for data structures like trees where you might have parallel evaluation, or you might have things that don't necessarily come after each other, but have a hierarchy or some kind of general order you can follow. You can also implement for loops and while loops with recursion, but you gotta watch out because you're not guaranteed to have enough stack space to actually iterate over stuff. So you might blow your stack, you might get a stack overflow. So if you noticed, in every single case there, we had generally evaluation order, and we also had lots of dependencies. So in this case, sum was a dependency and I was a dependency. In this case, condition was a dependency, count was a dependency, x was a dependency in both cases. So you really gotta consider, do we need to do these things in order? Is it always necessary? What if order doesn't actually matter? This brings us to the map function. So like I mentioned before, iteration in mathematics is applying a function repeatedly. So what the map function in Python allows us to do is apply the map function repeatedly, basically once per element in a collection, and produce a new collection where it's the results of applying that function. The map, it applies it to everything, it produces a new collection. The collection comes out in the same order as you gave it, but you don't have to do the evaluation in order in a map. Although in Python by default, it will do this. It'll do it in order. So here's a map example. We've got a list, v equals 1, 2, 3, and we've got a lambda, where the first parameter is x. We add x plus 1, that's the result. And we apply it to v, we would get 2, 3, 4. And v would still be 1, 2, 3. So v was not mutated, not changed at all. We could define this function base name, where we want to get the base name of a file, like its file name rather than its path name. So we split the path, and we take the last element. We could throw it in the map, so we go map base name, and this was our input, and we'd get home, nothing, and local. So we get the last element of the path. The map is oftentimes useful for things like, say, getting our URLs here. I've got a list of 3 URLs. I make get URL, which gets the contents of a web page, and then I pass it to map. And map goes ahead, calls get URL on each of these, and produces a web page. The neat thing about this is base name doesn't depend on v. Base name doesn't know about v. In this case, the lambda doesn't know about v either, and in this case, URLs, get URL doesn't know about them. There's no dependency there, but each element will be passed in separately. So these blocks are unaware, they're not dependent. This allows us to take advantage of that property and to parallelize map. So if you think in the kind of map reduce kind of sense, If you can do it with a map, you can generally parallelize with the map. If you limit the dependencies of a block, you don't make them reliant on globals, you don't make them reliant on mutation, you can oftentimes parallelize that computation. So here I've imported multiprocessing, I've made a square function, I've made a processor pool here, and then I can call p.map, which looks pretty well the same as the old map, except it will probably spawn this off to about 8 processors if we have them. And it will spawn it off across that range, and then it will produce a value u, and the length of u will be the same size as that range. It'll be every single value in that range squared. And it will do it in parallel. Now, you're thinking, well, Python and threads, and Python's not really that fast, maybe I'll use NumPy. Numerically, maybe I won't do this. But one thing you probably do a lot of times is accessing files, is accessing the network. So what you could do is you could parallelize your getting of URLs. You could say, I want to get at least 8 URLs at a time. We'll use a parallel map and throw the URLs in and get them in parallel 8 at a time. That way, with all that I/O running, Python will probably be able to handle it and we'll be able to come back in time. And we'll make gains in terms of runtime because these gets will be in parallel. So we can actually gain. So for I/O, it's great, like manipulating a directory of images, calling up extra functions, things like that. Another useful thing to know about is reduce. Reduce takes a function that takes 2 arguments and calls it across a list. So here we've got operator add, we've got a range, and we'll produce a list of squares, and what we'll do is we'll produce a sum of squares. Reduce reduces a list into one value via this function, and it repeatedly applies it. So basically, this thing right here, reduce, operator add, is the same as calling the function sum. These 2 are equivalent. Those 2 will be added together. Reduce is oftentimes used to convert a list into a single value, basically collapse a collection into a result. Even reduce can be parallelized in some scenarios. In the case of summation, it doesn't matter what order we do the sum, and we can also break the sum up into smaller parts. So we can have our parallel square right here, where we do a p-map on a square, and we square a list of values. And here, we can actually break that list of values into 2 parts. So we just get a range, the first half, the second half. And we say, please do that in parallel. P-map that, give it sum. So it asks for the sum of this and the sum of this, does that in parallel on 2 processors, returns a result. So in some cases, you can even parallelize your reduce. Now you'll notice I use sum there instead of reduce. Well, that's just because you can, the reduction on an add is the same as sum. So it's reducible. All right, one thing to think about, if your problem can be modeled as a tree, then this whole map reduce paradigm works really well. You can partition very well. So if you have a commutative or associative kind of problem, where the order of the application doesn't matter, as well as you can move the parentheses around, the commutative part, or the associative part, then you can break it down into a tree in just about any way you want. And then the different branches can be executed in parallel. So in this case, we could have a sum that operates across 3 values and gets the subsums of these and sums them all together. Okay? One thing to watch out when you're doing tree stuff is sometimes initializing values will hurt you, because then you get a dependency on the initial sum. So in this case, if we start off with a sum of 0, we'd have to pass this down. When you think about a sum, you don't actually have to initialize with 0. If you have 2 elements in a sum, or 1 element in a sum, you don't need to add 0 to them. You have that value. So you can avoid the dependency on the initialized value. So consider if your problem is decomposable into a tree. So in conclusion, I covered the very basics of iteration in Python, for, while, iterable, which use in for loop, recursion. Then I covered some of the functional ones like map and reduce. I showed that reducing dependencies into blocks, especially blocks with limited dependencies, allows iteration to be parallelizable. And you should really consider if in-order operation or strictness is necessary for your task, because if it's not, oftentimes you can simplify and parallelize. So if you can represent it as a function that doesn't have a lot of dependencies, then it's usually mappable. All right. So any questions about that?
Curious to know if you use a multi-processing pool and you specify more processes, then is it restricted in the number of processes you have on the box you're using?
I don't know the details of that, but I'll just make an assumption, but I don't know the details.
Okay.
The assumption would be that it forks off that many processes.
Sure.
So if you have n equals 8, it probably forks off 8. So in the case of doing HCB gets in parallel, I assume, I'm not necessarily right, I assume you'd get 8 processes running at the same time, which for an I/O bound process is probably okay, especially a network I/O bound process where there's multiple drives, multiple machines involved.
I guess my follow-up would be, does a multi-processing pool just have a provision for like, just give me whatever the machine can handle? If there's 8, just give me 8 or 4 or something.
I think it does, but I'm not sure. I was browsing it very quickly.
Might be a good question here. So, if you're using dependencies and blocks allows the integration to be parallelized, I've used some libraries before where I've tried to have multiple processes, and I've never had to do the math thing, and I'm trying to understand why that reduction of dependency is useful, and maybe that's just where I'm.
So the problem here is if we have dependencies, then when we map, especially using multiprocessing model, when we fork, we'll be forking the current value of sum.
Right.
So then when we come back, we have to make sure we update with that current value. And what will happen is, if I fork here, sum is 0. So if I fork 4 times right here, we get 4 copies of sum equals 0. So sum can't really come back, right? So if we can avoid these external dependencies, like this could be a file handle, this could be a current part of a calculation, even if we put like a placeholder there, like will be answered later, that could reduce our dependencies and allow us to parallelize. So we could even give a partial operation, we could give a partial value back saying, this value plus this operation plus whatever you got. So the dependencies here are a problem because they require update. They're being mutated. Whereas in the map, in the map sense, there's no dependencies. This only depends on its parameter here, right? And that parameter is just going to be one element from the collection you're going for. It's not, you're not doing a global update of something. So the lack of dependencies allows you to apply those functions independently of each other. And when you can apply them independently, oftentimes you can apply them out of order. But if you had some state in there, like keeping an iterator like count++, it would get weird and you'd require more communication between functions. You'd increase the dependencies and it would complicate the parallelization and the concurrency. You need to share that information. So it can get a little complicated. I hope that answered it.
Would it maybe make sense for people starting out with this to like draft in the graphic explicitly in a function and then only depend, like make it very clear when you're about to map something that here's just the function I'm passing in, and it's just here are the input parameters and it gives me enough quotes. As like sometimes if there's no function there, you're mapping it out, or like on that the for loop that you had there. If you don't, if the inner portion of the for loop was just wrapped in a function,
Yeah.
then that might be clear to see when you can parallelize.
Right. So if you're so imagine taking this block and put it into a function. This block in a function would be pretty well that, and it would imply that the function is dependent on this global S, or at least some S in scope that it can have access to. The function probably shouldn't be doing that. What you probably want is, in that case, you're doing a reduce. So you probably want the function to be dependent on some value that it adds to. So by trying to rewrite it as a function, oftentimes the dependencies come out because you'll need access. So if you don't want it to be bound to a specific S, you'll have to figure out some way of doing it. And sometimes that will mean S will become a parameter to your function. And then that way you've made your dependency explicit, and that way it's easier to map. Is that clear? Okay. Any other questions?
So you've definitely shown how we can use this idea of
we recognize a problem with this structure, let's say we recognize a problem that can be represented using map, potentially parallelized, but we don't expect to receive a great performance gain. Do you think for style reasons, it's maybe best not to use map and to use a for loop, or do you lean the other way and say no? If you express it as a map, it's good to use map because then it's very clear. You make more clear the structure of the problem, the fact that this function has no dependencies. See what I'm asking?
Yeah, okay, so I think it depends on the context. If you're with a team and they're not used to map,